Okay, let's get into this. We are taking a really deep dive today into some of the most consequential material coming out of architecture and engineering schools right now.
We really are.
We're looking at a daily lecture and assignment. This is straight from the Design and Build School of KING-KAMBUF.
DBSK, yeah.
Specifically, it's Year 3, Semester 2, course ARC 533. So, building science and enclosure systems.
And this is not, your standard course on just making things look good.
No, not at all. This isn't about optimizing floor plans. It's really about optimizing human survival in the face of, well, climate instability.
That's it. That is the reality of the profession now. Our whole focus today is on how you design urban mid-rise housing using what they call mixed-mode ventilation and high-performance enclosures.
And it's this amazing convergence point.
It is. This is where architecture, engineering, planning, public administration, and even construction management, they all have to come together. The stakes are just immense, especially in our big, dense cities.
And here's the thing that really grabbed me. The foundational idea that seems to guide this entire program, this whole integrated master's to PhD track.
The call to action.
Exactly. It's this idea that the master architect builder statesman designs buildings that actively protect the public.
It's a powerful statement.
It's not passive. It's not just, oh, I hope it's safe. It's an active, a mandate.
Exactly. When we talk about building science at this level, this is what a public promise looks like in built form. We're designing for the absolute worst-case scenarios.
Like what, specifically?
We're talking about those crippling urban heat waves that last for days. We're talking about wildfire smoke events that can just blanket entire regions for weeks.
And the grid going down.
And the energy volatility, the threat to grid stability, the way the building's facade, its windows, the air barrier, and the ventilation system, how they all work together.
Right.
That is the ultimate determinant of health, comfort, and safety for every single person inside.
So we're really describing a kind of sophisticated machine. It has to be tough enough to handle these external shocks, but also smart enough to constantly adapt.
A very good way to put it.
And that requires two critical components, which I think we need to define right off the bat. First, what exactly is a mixed-mode system?
So a mixed-mode system is really about the intelligent combination of natural and mechanical systems. It's a strategy.
Okay.
The idea is you primarily want the energy savings and, the psychological benefits of natural ventilation.
Just opening the windows.
Just opening the windows. But, and this is the key, you always have the fail-safe of filtered mechanical ventilation ready to go.
So it's not a choice between one or the other?
No, not at all. The goal is to have a brain, a control system, that knows precisely when and where to switch between them. The end result has to be high indoor air quality no matter what's happening outside.
And the second piece of that puzzle, the high-performance enclosure. That's the physical structure that lets that brain work properly.
Correct. The enclosure is the building's armor. It's the highly insulated, meticulously sealed shell that just drastically reduces the building's appetite for energy.
And that's what enables what you call passive survivability.
Critically, yes. By being high performance, the building stays stable. It stays habitable for a crucial period of time. We're talking potentially days during a complete grid outage. It protects people when all the mechanical systems go silent.
So the shell is the prerequisite for the whole thing to work.
You can't do it without the shell. It all starts there.
We're pulling all this from an academic setting, but the mission here, for you listening, is to really synthesize this rigor into something actionable, into immediate insights. Let's look at how these students are actually taught to get from the theory to a real design. Okay, so the curriculum jumps right in with a design question. And I love how it forces this functional mindset from the get-go.
It's a great question.
It just asks, how does your building breathe under heat, cold, and smoke?
See, that immediately shifts the focus. It prioritizes public health and resilience over, the typical aesthetic concerns you might start with.
It's the essential first step.
It has to be. Before you even think about picking a window or sizing an air conditioner, you have to analyze the environment.
Right.
This shift from just thinking about massing and form straight into a deep climate analysis, it's just non-negotiable for high-performance design. You have to have a rigorous, data-driven understanding of the local conditions to even know if mixed mode is feasible.
Or if it's just a nice idea that won't actually work.
Exactly. Or if it's just wishful thinking.
So when we say climate analysis, What specific factors are we talking about here? I'm guessing it's more than just looking up the average summer high.
Oh, absolutely. The source material is very clear. There are 4 factors they consistently prioritize.
Okay.
First, you've got dry bulb temperature. That's your basic air temperature. It sets the boundaries for heating and cooling.
Simple enough.
Second is humidity. This one is huge because even if the temperature feels pleasant enough to open a window, high humidity could mean you're bringing in a massive moisture load.
Which leads to mold and comfort issues.
Right. So you might need mechanical dehumidification even when the temperature is fine.
So those two kind of set the stage, but the next two feel like they're really crucial for the mixed mode strategy. The first one is diurnal swing.
Yes, the diurnal swing. That's simply the temperature difference between the day and the night.
And why is that so important?
Well, if you have a big temperature drop at night, say 25 degrees or more, that opens up these incredible opportunities for what we call night flush cooling.
So you're just using the cool night air.
You're using free cooling. You open the building up when it's, say, 60 degrees outside, and you flush out all the heat that built up during the day. You're using 0 mechanical energy to do it.
And that strategy really maximizes your natural ventilation periods and drives down your overall energy use.
Dramatically. It lowers your EUI, your energy use intensity, which is a key performance metric.
And the final piece is the kinetic energy of the environment, the prevailing winds.
You have to understand the wind, its strength, its direction, that allows you, the designer, to properly orient the building and place your openings to maximize cross-ventilation.
So you could mess this up pretty easily.
Oh, totally. If your primary cooling winds come from the northwest, but all your operable windows face south, you've just wasted a massive opportunity for free cooling. You have to design to leverage the local climate, not fight it.
There's a real dilemma here, though. Natural ventilation is obviously super desirable for energy savings, for that connection to the outside.
Of course.
But in high-density urban housing, it's always complicated. What are the major constraints that you have to weigh against that?
The constraints are all about public health and comfort. We just aren't designing in a vacuum anymore.
Right.
The immediate trade-offs are noise pollution. You've got constant street traffic, trains, construction, and then increasingly air pollution.
So opening the window isn't always a good thing.
It can be a terrible thing. If opening that window means a resident is dealing with 70 decibels of noise, or worse, particulate matter, PM 2.5 from wildfire smoke, well, then the system has failed its core mission. The building has to have a reliable way to get quiet, clean air.
This conflict, the desire for fresh air versus the reality of urban pollution, that seemed to be why this concept of the climate traffic light diagram is so important in the curriculum.
It is. It's a tool for visualizing and, more importantly, managing that transition between modes.
It's an operational roadmap.
That's a great way to describe it. Instead of thinking of the system as just on or off, the traffic light maps all the possible conditions into 3 distinct zones. And each zone dictates the right ventilation strategy.
Okay, walk us through them. Let's start with the ideal, the green zone.
The green zone, that's your operational sweet spot. Your dry bulb temp and your humidity are right in the comfort band.
So maybe 72 degrees, low humidity.
Exactly. Typically 68 to 76 degrees Fahrenheit with relative humidity below 60%. And crucially, the outside air quality is excellent low PM 2.5 and the noise is manageable.
So in that zone.
In that zone, the building is in its most natural, lowest energy state. Windows are open, the occupant is in control, and the mechanical systems are basically just dormant, maybe running some minimal exhaust.
But then conditions change. We enter the yellow zone. And this is where the intelligence of the system really gets tested.
The yellow zone is that transitional space. It represents marginal conditions where the system has to make smart decisions.
You mean example?
Okay, so maybe the temperature is still moderate, but the afternoon sun is just hammering the west side of the building, creating a big heat gain that needs localized cooling, or maybe the humidity is starting to creep up, or there's a temporary construction project next door making a lot of noise and dust.
So it's not a simple on-off situation.
Not at all. The system goes into a hybrid mode. The units on the quiet courtyard side, they might still be using natural ventilation, but the units on the noisy street side, they could be automatically sealed up, relying on filtered mechanical air. This zone demands really complex control logic and very accurate sensors.
And finally, the conditions that demand you batten down the hatches, the red zone.
The red zone is non-negotiable. It's triggered by extreme conditions. Deep winter cold, which drives huge heating loads. Peak summer heat, driving high cooling loads. Or, and this is the big one, a critical public health threat, like a severe pollution event.
Like wildfire smoke.
Exactly. When the air quality index, the AQI, spikes because of wildfire smoke, or when the outside temperature forces the mechanical system to run at max capacity, the enclosure has to be airtight. The air supply has to be 100% mechanical and very, very highly filtered, period.
It sounds like this climate analysis isn't just some preliminary step. It's a design input that has a huge impact on the budget, right?
It has to.
I mean, if you find out your city spends 70% of the year in the yellow and red zones, your whole budget allocation has to shift dramatically.
Precisely. If your building is in, say, Phoenix, or in a wildfire-prone area like San Francisco, places where red zone events are frequent and predictable, investing heavily in natural ventilation features might be, secondary.
Your priority is elsewhere.
Your primary capital spending has to be poured into that high-performance enclosure to keep the heat out and into robust, reliable, highly filtered mechanical systems. But if you're in a mild climate, like coastal California, then you can justify putting much more emphasis and budget into things like courtyards and operable shading to maximize natural ventilation.
And that early analysis, that's what addresses that first learning objective, determining if it's even feasible.
Right. It avoids the trap of designing a beautiful mixed-mode system that can only actually work 10% of the time.
Okay, so we know what the climate is going to throw at the building. Now we have to actually build the machine itself, the high-performance enclosure. This is that first line of defense, right? It locks in performance passively before you even turn anything on.
That is the critical mindset. If your enclosure is leaky, if it's porous or poorly insulated, you're just signing up for oversized, expensive mechanical equipment that will never, ever achieve real comfort or efficiency. The passive parts have to do the heavy lifting.
Which brings us to this concept that every architecture student learns, like it's gospel. The 4 control layers, the architectural firewall.
It's non-negotiable, and we teach these layers in a specific sequence because they manage physical phenomena that, if you ignore them, lead directly to building failure.
Okay, layer 1, water control.
Simple. Keeping liquid water out. This is your rain screen, your flashing, your sealants, the whole meticulous drainage plan.
And if you fail here?
Failure here leads to immediate material degradation. You're talking rot, mold, structural failure. It sounds basic, but managing bulk water is still the #1 reason for construction failure and warranty claims.
Okay, layer 2, air control. This is the air barrier. This feels like the superstar of high-performance design because of what it prevents.
It's probably the most misunderstood layer in conventional construction. The air barrier prevents uncontrolled air movement.
And what's the big implication of that?
The implication is that it directly stops convective heat loss.
Explain that.
Okay, imagine air leaking out of tiny gaps around your windows or where the wall meets the ceiling. That air is carrying heat energy with it. Convective heat loss can be a massive percentage of your total energy waste.
So warm air leaks out in the winter, hot air leaks in during the summer.
Exactly. The air barrier is that continuous sealed layer that just eliminates that wasteful exchange.
And we often confuse that with layer 3, which is vapor control. This manages moisture diffusion. What's the real difference there?
So air control is about airflow. Vapor control is about moisture traveling through the materials themselves as a gas-water vapor.
Okay.
Vapor movement is driven by differences in vapor pressure. And if you get the placement of your vapor retarder wrong, say you put it on the wrong side of the wall for your climate zone, you can trap moisture inside the wall cavity.
And that's bad.
It's a disaster. It leads to condensation, chronic mold issues, even if your exterior rain screen is perfect. This is why the foundational building science texts, like Straub and Burnett's, they just hammer this point home.
Yeah.
You have to understand heat, air, and moisture all at the same time. They're all connected.
All right. And the final layer, number 4, thermal control.
This is your continuous insulation layer. It manages heat flow through conduction. So we're trying to minimize heat conducting across the wall assembly. This layer is what ensures the temperature difference between inside and outside doesn't translate into high energy bills or uncomfortable interior surfaces.
And the key here is making sure that insulation is continuous.
Yes, and avoiding the Achilles heel of the modern building, thermal bridging.
Let's stop on that for a second. For you listening, if you're not an engineer, what is a thermal bridge? What does that failure actually feel like?
A thermal bridge happens when a highly conductive material, usually it's metal studs or a concrete slab edge, it punctures through your insulation layer. It creates a little highway for heat to just bypass all your thermal defense.
So in a mid-rise building.
In a mid-rise, if the enclosure is poorly detailed, that concrete slab edge which runs from the warm interior through the wall to the cold exterior, it becomes a massive thermal radiator.
You could actually feel it.
Oh, absolutely. In the winter, you could stand next to the wall right where the slab hits, and that spot will be noticeably colder to the touch than the rest of the wall.
And that cold surface causes problems.
It causes radiant discomfort, so you just feel cold standing there. And it often leads to condensation buildup right where the warm, moist interior air hits that cold bridge. It's an energy loss, a comfort failure, and a durability risk, all in one little spot.
So that emphasis on continuity at the windows, at the slab edges, that's really where the design battle is won or lost.
Design is detail, 100%. The performance of these four control layers is only as good as their continuity. It's a chain. If you have a perfect air barrier everywhere except for a tiny gap where the wall meets the window frame, that tiny gap becomes your single largest point of air leakage. It just nullifies all the effort everywhere else.
So this requires specialized work.
Specialized detailing, specialized installation, and meticulous quality control on site.
Now let's get into quantifying this performance. Students have to meet and exceed codes. This gets into that second learning objective. What are the key quantitative targets here?
Okay, so now we're moving into the specs. We're talking about U values. A U value measures how quickly heat transfers through a component. A lower U value means better insulation performance.
And the building codes set a minimum.
Right. Codes like the IECC or ASHRA 90.1 set minimum U values for walls and windows. High-performance design always aims to be significantly better, meaning lower than that minimum.
And especially in a glassy urban building, you have to worry about the sun. So that means tracking the SHGC, the solar heat gain coefficient.
The SHGC is absolutely crucial. It's the fraction of solar radiation that actually passes through the glass.
And why is that so important for managing cooling?
If you use standard glass on a big south or west-facing facade, you are basically installing a giant free heater in the space. It brings in massive amounts of heat, which forces your cooling system to fight that load all day long.
Wasting a ton of energy.
A ton. So specifying a low SHGC glass, often we're talking below 0.25, is essential to keep the building passively cool and prevent the mechanical system from being massively oversized.
And the last big metric, the one that really separates the high-performance projects from the code minimum ones, is air tightness, which we measure as ACH 50.
ACH 50, it stands for air changes per hour at 50 pascals.
Okay, break that down.
So 50 pascals is a standard pressure difference we use during a blower door test. It simulates a steady 20-mile-per-hour wind pressing on the whole building.
And you measure how much air leaks out.
You measure how many times the entire volume of air inside the building gets replaced per hour under that pressure. A code minimum building might be around an ACH 50 of 5.0. A high-performance building is pushing for below 3.0 and often below 1.5.
That's a huge reduction in air leakage. But what does it actually take to hit a 1.5 ACH 50 target in a complicated multi-story building? It's not just using standard drywall on tape, is it?
No. It's a monumental construction effort. It requires total quality control.
So what are the materials?
To get that tight, you're designing with specialized materials. You're using liquid-applied membranes that seal the exterior sheathing. You're using special tapes that have to be meticulously rolled and pressed onto every single seam and junction. You're using dedicated air-sealing gaskets around every single penetration, every pipe, every vent, every electrical wire that goes through the wall.
And you had to test it.
You have to. It requires third-party inspection and that mandatory blower door test. That test verifies that your air control layer is actually continuous and it's working as designed. You can't hide leakage when the building is under 50 pascals of pressure. The leaks show up.
So hitting those low ACH 50 numbers directly proves the success of your air barrier.
Absolutely. If you get high air tightness, you've minimized uncontrolled infiltration. And that means every cubic foot of air that enters that building is clean, it's filtered, it's conditioned, and you're not wasting energy heating or cooling the street.
All right, so we've built this sealed, robust armor, the high-performance enclosure. Now we have to install the intelligence that lets it breathe. We're moving into the mixed-mode typologies, the physics of airflow. This is learning objective 3, right? Diagramming the paths.
Exactly. We have to categorize how the building breathes into both natural and mechanical modes, and the design has to account for both. Let's start with the two primary natural modes.
First up, cross-ventilation.
This relies purely on external factors, wind pressure, basically, and it requires really careful planning to make sure air can travel horizontally through the unit.
Which means you need openings on at least two sides.
At least two sides. In a mid-rise building, this usually dictates your whole unit layout. You're trying to ensure, for example, that one side faces the street and the other faces a protected courtyard, or that you have corner units that can grab wind from two directions.
Okay, and the second natural mode, which you see more in taller structures, is the stack effect. This is just basic thermal physics, right?
It's pure physics. The stack effect is driven by temperature-induced buoyancy.
Meaning hot air rises.
Hot air rises. Warm air is lighter than cold air. So if you create a continuous vertical pathway, like a shaft or a stairwell, or even just the building envelope itself, and the air inside is warmer than the air outside, that warm air will rise. It gets exhausted through openings at the top, and that naturally pulls cooler replacement air in through openings at the bottom.
So it's like a natural engine.
It's a massive resource for energy-free cooling and ventilation. It's a powerful engine that works with no moving parts, just gravity and a temperature difference.
But when conditions force us into that red zone, we have to rely on the machines. And the source material highlights some specific high-performance technologies for that.
Yeah, the key shift in modern design is separating your air conditioning from your ventilation. For ventilation, we now rely on a DOAS, which is a dedicated outdoor air system.
How is that different from a traditional AC unit?
Well, traditional AC often just cools and recirculates the interior air, and it only brings in a tiny bit of fresh air from outside. A DOAS supplies 100% fresh, fully conditioned, so that's heated, cooled, dehumidified, and filtered outdoor air. And it does that independently of the system that handles the room level temperature.
So you can guarantee the air is actually fresh and clean.
We can guarantee that we're meeting the safe, clean air delivery rates that are mandated by code, no matter what the temperature needs of the room are.
And what makes that DOAS system affordable and efficient, especially in, say, a really cold or hot climate, is the HRV-ERV, a heat or energy recovery ventilator.
The HRV, or ERV, is the energy recycling engine. It's brilliant.
How does it work?
As your warm, stale, dirty air is exhausted from the building, it passes through a special core. And in that core, its heat, or its coolness in the summer, is transferred to the incoming fresh outdoor airstream. But the two airstreams never actually mix.
So you're just capturing the energy.
You're recovering 60 to 80% of the energy that you would have otherwise just thrown away. In the winter, it means you don't have to spend a ton of energy heating up frozen incoming air. In the summer, you're not spending it cooling down hot, humid incoming air. If you want to hit low EUI targets, a recovery ventilator is completely non-negotiable.
So we take all these modes, natural, mechanical, and we combine them into the hybrid system. What are some of the critical hybrid mode strategies the students have to detail?
Well, there are temporal strategies like seasonal switching. You might go full mechanical during the absolute coldest parts of winter and hottest parts of summer.
Right.
But more importantly, there are zonal strategies. So you might have a building where the units on the quiet courtyard side are designed to be in that green zone operation as much as possible, maximizing natural ventilation.
But the street side is different.
But the units facing a busy, noisy street, they might be designated to be in mechanical mode 95% of the time, and that means you have to design that facade with enhanced acoustic attenuation just to make them habitable.
So you're designing for different conditions on the same building.
You are, and that requires some really complex control sequencing to manage it all.
Let's get to the integration piece.
Mm-hmm.
Envelope HVAC integration. You have to explain why the high-performance enclosure must be designed before you size the mechanical systems. So this seems like it would be a constant fight on a project schedule.
It is a constant fight, because design teams often work in their own silos. But the financial reality and the functional reality, they just mandate this sequence. The primary outcome of a great enclosure is load reduction.
Reducing the workload for the machines.
Exactly. Every single dollar you spend on continuous insulation, on low SHGC glass, on air tightness, it directly reduces the building's thermal load.
And when you reduce the load?
When you reduce the load, the resulting mechanical systems, the chillers, the boilers, the heat pumps, the fan coils, they can all be significantly smaller.
Which saves money up front.
Immense capital cost savings. If you size a system based on a leaky code minimum envelope, you are installing a huge, expensive system that's going to run inefficiently for 50 years. If you invest in the envelope first, you can right-size the system, saving construction money up front and dramatically lowering your operating costs for decades.
It's an elegant feedback loop.
It is. The passive design shrinks the active components.
The source material also pushes beyond just temperature toward this idea of full thermal comfort. That includes that intangible feeling of being comfortable right next to a window or an exterior wall.
Right. We define thermal comfort as more than just the air temperature. It has to include radiant comfort.
Okay.
A high-performance wall with continuous insulation ensures that the interior surface of that wall stays very close to the air temperature, even on a freezing day.
So you don't feel that cold draft.
It eliminates that drafty, cold feeling you get standing near a leaky window or cold wall. It actually changes how you can use the interior space. We also have to integrate controlled airflow, making sure fresh air moves gently enough to ventilate without creating annoying drafts.
And none of this highly controlled breathing works if the occupant can just sabotage the whole system. This brings us to the smart systems and controls that manage the switching.
The control logic is the brain.
Yeah.
And the simplest but maybe most critical control is the window sensor or interlock.
To stop people from running the AC with the window open.
It prevents the ultimate waste. Running the air conditioning or the heating while a window is wide open. If the window opens, the system in that zone has to immediately pause its conditioning cycle.
It seems so basic.
It's basic logic, but you'd be amazed how often it's value engineered out of a project, leading to massive energy hemorrhages.
And given the need to switch into that red zone during, say, a smoke event, the building needs to be monitoring the air, not just the weather.
Yes. High-performance buildings use sophisticated monitoring. We rely on co-euro sensors to measure indoor air quality related to how many people are in a space. That can trigger a boost if the air gets stale.
But now you need more.
Now, critically, we have to rely on PM 2.5 monitoring. PM 2.5 is that fine particulate matter from smoke. If the sensor detects high PM 2.5 levels outside, or if a unit is struggling to maintain low levels inside, the system has to automatically lock down and ensure its high-level filtration, like a MER V13 filter or higher, is running at full capacity.
That's the definition of the building actively protecting its residents.
It is. It's the promise in action.
So we've laid out the science. But the curriculum is really clear that the architect-statesman has to view all this science through the lens of social responsibility.
Yes.
The leadership minute cited in the source material states it so clearly. Resilient design is a public promise that the building will remain safe long after the grid fails. This takes us way past simple efficiency and into, well, existential safety.
This section, resilience, health, and equity, this is where the ethics of building science really become clear. We have to analyze passive survivability. That's the ability of the building to stay habitable when the power is out and the machines fail.
Okay, give us a tangible scenario. Let's contrast failure versus success. What happens during a summer heat wave when the power goes out?
Okay, let's contrast two identical mid-rise apartment stacks during a 3-day 100-degree heat wave and a blackout. The code minimum building, with leaky windows and minimal insulation, it acts like a poorly sealed cooler.
So it heats up fast.
Its internal temperature will rapidly track the external temperature. Within, say, 8 to 12 hours, that apartment could easily hit 95 degrees inside. That's dangerous, especially for vulnerable people.
And a high-performance building.
Because of the air tightness, that low ACH 50, and the continuous insulation, the low U values, the heat just gets in so much more slowly.
Right.
The high-performance unit might rise from a starting point of 75 degrees to maybe only 82 or 84 degrees over the first 24 hours. Maybe it stabilizes around 90 degrees after 48 hours.
That 10 or 15 degree buffer is huge.
It's critical time. It ensures the building remains a relative refuge for 2 or 3 days. It buys time for relief or for the power to come back on. That is the literal difference between safety and an emergency evacuation.
And beyond just temperature, resilience also depends on maintaining healthy indoor air quality, IAQ, during emergencies.
This is the modern climate imperative: power outages and wildfire smoke events. They are often correlated or they happen at the same time.
A dangerous combination.
A very dangerous one. If a building relies only on natural ventilation, the second a smoke event happens, the residents have to close their windows. And then they're just relying on whatever air is trapped inside, which degrades very quickly.
But the resilient building has a plan.
The resilient high-performance building maintains a small power reserve, maybe from solar and batteries, or a small emergency generator that is dedicated only to running its filtered mechanical ventilation system.
So even in a blackout.
Even in a blackout, the building can still seal itself off and provide filtered, life-saving air quality, protecting everyone inside from the toxins outside.
This leads us right to the equity checkpoint, which is a really powerful ethical challenge in the source material. If we're designing based on these zonal conditions, different performance for different sides of the building, we run the risk of creating unequal living environments.
This is the core ethical challenge for the architect-statesman. If, for energy reasons, we decide to only allow natural ventilation, that green zone operation, on the quiet courtyard side, what happens?
Those units become more desirable.
Those units might be quieter, they feel fresher, and they could potentially command a higher rent. Meanwhile, the units on the busy street side are constantly sealed up, relying on the mechanical system. They might be exposed to more potential noise and maybe even higher utility costs if the building isn't managed perfectly.
So what's the mandate here? What are the architectural decisions you have to make to ensure there's parity?
The mandate is crystal clear. All residents deserve clean, safe indoor air, especially during emergencies. You cannot build a two-tiered system of premium clean air units versus polluted but cheaper units.
So how do you avoid that?
To ensure parity, the designer has to invest in specific mitigation measures for that less desirable side.
Like what?
It means investing in specialized acoustic attenuation. That means thicker glass, more complex window framing, noise-dampening facade layers on the street side, so that when the windows are open, the noise is minimized. It also means ensuring that the mechanical system, the DOS and the HRV, delivers the exact same high standard of filtered air, say MRV13 filtration, to every single unit, no matter which way it faces.
So equity is designed into the facade itself.
You have to design it in. You can't add it on later. That 15% valuation weight that the assignment gives to ethics and community, that just underscores that this is a critical test of leadership, not just engineering.
Okay, let's talk about the elephant in the room, cost. Superior performance is so often just dismissed as a budget killer. The final intersection here is finance and value capture, and it makes the case that this is actually a smart business decision.
The whole conversation has to pivot. It has to go from added cost to essential investment. The pro forma data that's cited in the sources is essential here because it's what allows the architect to win the argument against value engineering erosion.
We see that the initial capital cost is higher, and it's concentrated in the enclosure. Can you review those key line items?
Yes. The exterior walls at $32 a square foot are more expensive. That's because they include continuous insulation and those better air and water barriers. The high-performance glazing at $26 a square foot is costlier because of low coatings and special gas fills.
And the mechanical systems.
Right. The DOE HRVRV units at $12 a square foot are an upfront commitment. Even the necessary envelope testing is a dedicated line item at $2 a square foot. So yes, the initial hard cost is higher.
But the immediate trade-off is that you need less HVAC equipment.
Absolutely. Because the building's load is so much lower, the cost of the internal heating and cooling equipment, which is listed at $14 a square foot, is significantly offset, or in some cases even reduced, compared to installing massive systems in a leaky code minimum building.
And the long-term return is huge.
It's undeniable. The annual operating costs, the OPEX, are typically reduced from around $6 a square foot down to $4.50 a square foot, year after year after year.
And the sustained reduction in OPEX, that's what provides the powerful LCC lifecycle cost justification you need to fight back against value engineering.
That's your weapon.
So how do you articulate that in that inevitable meeting with the person controlling the budget?
You have to frame the envelope investment not as a cost, but as prepaid energy and prepaid risk insurance. You prove that the $1 you invest in the enclosure today saves you $3 over the building's 50-year lifespan in operational costs, in reduced maintenance, and in avoiding catastrophic failure.
And it opens up other financial doors.
Yes. Superior performance qualifies projects for green financing products. It qualifies them for resilience bonds that lower the lender's risk, and you can get substantial utility rebates tied to energy savings. The LCC calculation turns the design requirement into a financial imperative. You literally cannot afford to cut the performance because you're cutting decades of savings and safety.
Okay, so we've translated the theory into these critical requirements for safety, equity, finance. Now let's just quickly look at how all this knowledge moves into tangible professional work. The DBSK assignment itself reinforces that performance isn't theoretical, it has to be proven.
The deliverables demand synthesis. The students have to merge the climate data with engineering specs and ethical considerations, and then produce professional documents that will actually dictate how the building is built.
The first deliverable is the climate context snapshot.
This is the concise justification. It has to analyze the local weather data, the TMY3 data, and the urban constraints to justify why they chose their mixed-mode strategy. It needs to quantitatively state the percentage of time the building will spend in the green, yellow, and red zones.
It sets the operational goals.
Exactly.
Second, the enclosure performance spec. This is the hard engineering.
This is the document with the numbers. The specific target U values for the walls and windows, the required SHGC, and most importantly, that target ACH 50 rating for air tightness.
Yeah, they had to draw it.
Critically, yes. They have to produce an annotated section detail showing the continuous connection of the water, air, vapor, and thermal control layers at a really complex junction, like where a window frame and a slab edge meet.
Third, the required mixed-mode diagrams. This proves they understand the air physics.
They need two diagrams. One has to illustrate the natural mode. It shows the cross-ventilation paths and the stack effect dynamics. The second one illustrates the mechanical mode. It has to show the location of the DOAS intake, the high-efficiency filtration path, and how the air is distributed, proving they know how to deliver clean air safely.
And finally, tying it all together, the performance and equity memo.
This memo synthesizes the impact. It calculates the projected EUI reduction. It sketches out the passive survivability duration, like this building will provide 48 hours of refuge. And critically, it justifies how the design ensures equitable environmental quality for all units, regardless of where they are on the facade.
And that 15% valuation weight for ethics and community.
It just shows that the technical performance is only acceptable if it's also socially responsible.
This level of analysis, it requires some pretty sophisticated digital tools. This is not pencil and paper design anymore. What's in the architect's toolkit today?
No, we rely on advanced simulation software. Tools like Climate Studio and Ladybug tools, they're often integrated right into design platforms like Rhino or Grasshopper. They let designers accurately model energy flows, calculate the precise U values they need, optimize shading devices.
So they can test things digitally first.
They can analyze daylight targets. They can use hourly climate data to predict the building's performance throughout an entire year, long before a shovel ever touches the ground.
And to make sure that the theoretical model actually matches the built reality, field verification is mandatory.
It has to be. The checklist includes budget for verification. We're talking about using smoke pens to literally see air leaks during construction. We're using infrared thermometers to find cold spots that betray thermal bridges.
And the big one.
And the mandatory non-negotiable blower door test to confirm that the achieved ACH 50 air tightness target actually matches the design goal. If the design promised 1.5 and the test comes back at 4.0, the construction team has to go back and seal the building before anyone can move in.
Let's just review that integration checklist quickly. These performance goals, they have to be embedded right from the very start of a project.
Performance is a sequence. In schematic design, or SD, you're focused on setting your preliminary U values and your overall glazing ratios based on that climate analysis.
Okay.
By design development, or DD, you're doing the rigorous energy modeling to lock in the required performance. In construction documents, or CD, the engineers are detailing the control sequences for the mixed-mode system and drawing the details for the air barrier continuity.
And finally, during construction itself.
Finally, in construction administration, or CA, quality is verified through commissioning, through training, and through those critical envelope performance tests. If you wait until CD to start thinking about air tightness, you have already wasted 90% of your potential cost savings.
And the biggest risk on any project's risk register is always VE erosion, the budget cutting away the essentials.
It is the perpetual conflict. The only defense against someone trying to value engineer out the air barrier or the continuous insulation or the high-performance glazing is that rigorous life cycle cost justification we talked about.
You have to come prepared with the data.
When the budget controller suggests cutting the envelope quality, the architect has to be ready with the data that proves that such a cut is an economic detriment to the owner and, frankly, a moral failure for the occupant. You cannot value engineer away safety and health during a climate crisis.
So this deep dive has really explored the demanding curriculum facing today's architects and builders. It showcases amazing integration of climate adaptation, engineering rigor, and social responsibility right at the urban facade. We covered the science of the high-performance enclosure, that continuous airtight armor that locks in resilience.
And we analyzed the wisdom of mixed-mode ventilation, that intelligent system that switches between energy-saving natural breathing and that sealed, filtered, life-saving mechanical air. It ensures continuous safety, even during extreme events like smoke or grid failure.
So what does this all mean for you, the listener? It means the definition of high-quality construction has fundamentally changed. The profession is being tasked with merging science, empathy, and governance to create what is essentially civic infrastructure. Buildings that actively shelter and stabilize human life, not just on the good days, but when global systems are under intense stress.
The Leadership Minute demands that we see this design work as a public promise. And if indoor environmental quality, the safety of the air you breathe during a wildfire, the habitability of your home during a power outage, if that is truly a human right that has to be delivered equitably, then we have to look beyond our immediate project boundaries. And this leaves us with a final provocative thought for you to consider. If these life-saving design strategies are proven, if they are financially viable through a life cycle cost analysis, and if they are ethically necessary, then how does your local governance structure, your city's codes, your local zoning incentives, your government's risk registers, how do they currently support or impede the mandatory integration of these high-performance features in housing? What are the institutional barriers that are preventing us from universally providing this level of safety and resilience to every resident in every new building? Think about that framework of governance next time you look at a building.